We have covered parallel and spent a lot of time here on parallel RLC circuits, but what happens when we get to series RLC circuit? And the answer is it's the same but different. So let's say that we've got this as our circuit. Let's put a switch down here at the bottom. There's a switch here. That switch is closed at t equals 0. So we've got some R value, some L value, some C value here. Now the capacitor has some initial voltage across it. So this is the natural response for a series RLC. Well, when that switch is closed, there's going to be some current that flows. Let's just call that current I. So the capacitor is initially charged, has a potential difference across the plates. At t equals 0, the switch is closed, current begins to flow. Using KCL, then we can write the voltage across the resistor, plus the voltage across the inductor, plus the voltage across the capacitor, has to equal 0. Well, the voltage across the resistor, that's I times R, plus the voltage across the inductor, that's L di dt, plus the voltage across the capacitor. Solve for that, and it's 0 to t of I dt plus whatever the initial voltage was. We've got a derivative integral together. You've seen this sort of thing before. How do we do it? We take another derivative of everything. So this is going to be R di dt plus L d squared I dt squared plus I over C, and that's equal to 0. Going to rearrange the terms. D squared I dt squared plus R over L di dt plus I over LC equals 0. And this is the equation of state for series RLC, for a natural response. Okay, you've seen this sort of thing before. The coefficients are certainly different here. You'll see there is a little bit of difference between the way the coefficients are put together. This is for I as well, and we've spent a lot of time working voltage equations and so forth for this. But if you were to go through, find the characteristic equation, assume a solution, find the characteristic equations, and go through exactly the same sort of thing, you're going to end up with 3, how many? 3 solutions here. There are going to be the overdamped, the underdamped, and the critically damped. You determine if they're over, under, or critically damped based upon exactly those same criteria that we had before. Is alpha squared bigger than omega squared, omega naught squared? But here's what you're going to discover. There is a difference here. And the only difference is in the Nieper frequency. We're not going to go through this. The Nieper frequency is going to be R over 2L. Now previously, alpha was 1 over 2RC. This is for parallel. This is for series. If you can make that distinction right there between those two, then everything else is exactly the same. So if you're able to solve one of the previous problems, then you're able to solve this one as long as you keep in mind that this is the difference right here. That's the only difference. So what does that mean? That means the current is going to be of the form I final plus the natural response. And the voltage, which voltage? Any one of them. So this is going to be V sub C or V sub R or V sub L. It's going to be V final plus the natural response. All right, now this is the natural response type. There's not a voltage source in here, so the final current here is going to be 0. The final voltage across everything Depends though. Final voltage across this is going to be 0 once the current dies. Final voltage across that is going to be 0 once the current dies. Final voltage across this though, well, what do you think is going to happen there? Okay. So something is going to change, and it may not be exactly that the final voltage is the same across every thing. However, in this case, it is going to be 0. The final voltage is going to be 0 across every one of those components. The reason is because this radiates away energy at a rate of I squared R. So that's energy leaving the system. Eventually, all of the energy is going to leave the system. That's the nature of the natural response, that the energy is decaying. Okay? All right, now that is the only difference. So let's work a problem. Let's work a series RLC problem. So we got a voltage source. Let's put a switch, an inductor, a resistor, and a capacitor. This is 6.25 microfarad. This is 250 ohms. This is 62.5 millihenry. And this switch is closed at t equals 0. And this is a 60 volt source. All right, what do I want to find? I want to find, pick something, V naught across the capacitor, right there. Okay, there's no initial energy present. This is the source. This is going to be a step response. Now, we didn't go over this, but you know how it's going to fall out. It's going to be V naught. This V naught here is going to be V final plus what goes in there? Natural response. Okay, now we just need to figure out what the natural response is going to be. We also need to figure out what the final voltage is going to be here. Let's think about that for a minute. Switch is closed at t equals 0. There's no initial voltage on the capacitor. However, at t equals 0, a current begins to flow, and at that stage, the capacitor begins to charge. Okay, the capacitor is going to charge up until its voltage reaches the same voltage as the source over here, 60 volts. So V final is going to be 60 volts for the capacitor. Okay, at t equals infinity, that's V final for the capacitor. That is not V final for the resistor or the inductor. And they depend upon the current, and the current is ultimately going to stop flowing once the potential difference across the plates of the capacitor equals the potential difference of the source, because the source doesn't have enough energy anymore to push more current around. Okay, so that's our V final right there. Let's figure out what our response is going to be. Alpha is going to be, it's no longer 1 over 2 RC, it's R over 2L. So that's going to be 250 divided by 2 times L, which is 62.5 times 10 to the negative 3. All right, do that calculation right there, and that turns out to be 2,000 radians per second, which makes alpha squared 4 times 10 to the 6. Omega naught squared is just 1 over LC, so that's 1 over L, 62.5 times 10 to the negative 3 times C, which is 6.25 times 10 to the negative 6. That turns out to be 2.56 times 10 to the 6. So what have we got? We've got alpha squared greater than omega naught squared. It turned out to be that way. So this is overdamped. So what does that mean? V naught is going to be 60 plus A1 e to the S1t plus A2 e to the S2t. Okay, so we know the general form. What about S1 and S2? S1 is going to be negative alpha plus the square root alpha squared minus omega naught squared. That turns out to be negative 800. S2, negative alpha minus the square root alpha squared minus omega naught squared. That turns out to be minus 3200. And you know what S1 and S2 are now. Okay, we need to figure out what our coefficients A1 and A2 are. You rely upon the initial conditions. So what is the initial condition? What is V naught at 0 plus going to be? Well, what was the initial voltage before t equals 0? And it was 0 because there was no energy in the capacitor before t equals 0. So immediately after t equals 0, it has to also be 0. Why? Because you cannot have an instantaneous change in voltage for a capacitor. Okay, so this is equal then to 60 plus this evaluated at t equals 0, which is just A1 plus A2. So there's one of our equations right there that we need to evaluate A1 and A2. The other one, dV naught dt, evaluated at 0 plus, that's going to equal I sub c evaluated at 0 plus divided by c. Okay, well, what is that going to be? Well, if you'll think about the fact that there was no voltage before t equals 0, no voltage after t equals 0, then you expect dV dt evaluated at 0 plus to also be 0. Okay, is that the case with the current? Well, initially at t equals 0, remember there's only one current here for all of these elements. At t equals 0, the inductor is going to stop any kind of current flow because it's going to create a back EMF that's going to, at least at 0 plus, not allow current to flow. So yeah, it does make sense that I sub c at 0 plus is going to be 0, therefore this dV dt is going to be 0 as well. Okay, and this is equal to the v function, the derivative of the v function evaluated at t equals 0. So this is going to be a1 s1 plus a2 s2. There is the other thing. So you've got your two equations, your two unknowns. You should be able to solve for a1 and a2 out of that. When you do that, a1 turns out to be negative 80, A2 turns out to be 20, and both of those have units of volts for this one. So what does that mean? That means now we can jump to our final solution for V. I'll write it right down here. V of t is equal to 60 plus A1, it's a negative, 80 e to the negative 800 t plus A2, 20 e to the negative 3200 t volts. There is our final answer for the voltage across that. Okay, now from that you should be able to go forward. Let's say you wanted I sub c. I sub c is going to be c dV dt, specifically V sub c right there. Okay, well, this voltage here is V naught. That is the voltage across the capacitor. So this is really V naught right there. So you take the derivative and you can get your answer for I sub c. Let's say that this is our circuit. So here's our capacitor. Let's say that that is 40 nanofarad. This is 2.5 millihenry. This is going to be 500 ohms. Here's the switch, and the switch is actually opened at t equals 0. This is a 300 ohm resistor and 80 volt source here. Okay, what we're interested in finding here is we want to know what is the voltage across that capacitor there, and let's say what this current is here. Okay, so we want to find V naught and I naught. Okay, so the switch is originally closed and opened at t equals 0. So it's been closed a long time before t equals 0. Now think about what's going to happen if that's the case. After the switch is closed for a long time, the inductor is going to behave like a piece of wire. So there's going to be a current that flows through here. Any current that flows through here is not going to be impeded by that inductor. Also, after a long time, this capacitor has become charged, and it's become charged to the point where no current's going to flow over here as well. Since there's no current flowing over on this side, because the potential across that has to be the potential at across those two nodes right there. And remember, after a long time, this behaves like a piece of wire, so the voltage across this is equal to the voltage across that 500 ohm. All right. So we could say this, that V naught at 0 plus is going to be 500 over 800 times 80. So there's the voltage across that. Let's do that calculation. And that turns out to be, I made a mistake. That turns out to be, let's see, 50 volts. All right. So we know what that is now. If I know that the voltage across that resistor is 50 volts, I could probably figure out what the initial current is at 0 plus, because that's the voltage at 0 plus. That current's going to be V over R. So let's see, that's going to be 50 volts over 500 ohms, and that turns out to be 0.1 amps. So that is what I naught is at t equals 0. I could have also gotten I naught just by figuring out what the current is around this loop here. So it's going to be V 80 volts over R 800 ohms. So that's another way to do it, and it would have given me 0.1 amps as well. Okay, so either one of those ways tells me the same thing. There is 1/10 of an amp through the inductor at t equals 0 plus. All right, now when that switch is opened at t equals 0, well then the circuit becomes this: resistor, inductor, capacitor. So 40 nanofarad, 2.5 millihenry, 500 ohms, and this is I naught, and we've still got V naught here. Okay, so we want to figure out what both of those are after t equals 0 now. Well, let's figure out which case we've got. Alpha, this is a series case, so this is going to be R over 2L, so it's going to be 500 over 2 times 2.5 times 10 to the negative 3. Do the calculation for that, 10 to the 5th. That makes alpha squared 10 to the 10th. Omega naught squared is 1 over LC, which is going to be 1 over 2.5 times 10 to the negative 3 times C, 40 times 10 to the negative 9. And that turns out to be 10 to the 10th. How about that? Alpha squared is equal to omega naught squared. So which case is this? Critically damped. All right, do you know the general form of the solution then? For both of our quantities, it's going to be exactly the same. Let's start with I naught as a function of time is going to be I final plus d1 t e to the negative alpha t plus d2 e to the negative alpha t. Almost ran out of room there. Okay, let's figure out what this I final is. I final. Now this is I final here. So here, what is that after a long period of time? Well, after a long period of time, remember this dissipates away energy, so it's going to die down. You expect that to be 0. Okay, well, if that's the case, then I naught at t is going to be equal to just d1 t e to the negative alpha t plus d2 e to the negative alpha t. And as t goes to infinity, the exponentials are going to win, and it's going to end up being 0. So that makes sense. All right, we could say that I at 0 plus. Well, let's think about that. I at 0 plus, that's this 0.1 that we've got here. So this is 0.1, and that's equal to, evaluated at t equals 0, first term goes away, the exponential goes to 1, so this is d2. So we've got d2 right now, right here. And then we need to do the same sort of thing to find out what d1 is. And you can think of this way. I naught at the derivative, we're going to have to use the derivative to get the other coefficient. So since we have I at 0 plus equal to that, I at 0 minus would have also been equal to that, because you cannot have an instantaneous change in current for the inductor, and there's only one current here after t equals 0. So what does that mean? That means that the derivative, when we evaluate it at 0, is going to be 0, okay? Because there is no change right at t equals 0. It goes from whatever it was before to whatever it is right after. So that's this value, the 0.1 amp. Okay, but it doesn't change. Now, let's take the derivative of this with respect to 0, and when you do that, you end up with d1 minus alpha d2. So here's our other equation. We know what d2 is. We should be able to solve for d1 out of this. And whenever we do that, we get d1 equals 10 to the 4th. Let's see. We've got d1, we've got d2. I think we're ready to just jump right in and say that I naught as a function of time is equal to d1 10 to the 4th t e to the negative alpha, which is negative 10 to the 5th t, plus d2, which is plus 0.1 e to the negative 10 to the 5th t amps. There. So that's what it looks like for our current. All right. Now we're also asked to find the voltage, and that's the voltage across the capacitor. You realize there's only one current for our loop here, so multiple ways to get it. We could say the voltage across the capacitor, which we've called V naught. Let's just leave it V naught. Is of this form: V final plus the natural response, and the natural response is going to be, you could name these coefficients anything you want, d3 t e to the negative alpha t plus d4 e to the negative alpha t, like that. Okay, so we need to figure out what our final voltage is going to be, and I believe we have already figured that out. It's going to be 0. We expect that because remember, the resistor is radiating away energy, so there's going to be no energy left to create a voltage across the capacitor. So V final is going to be 0. What about V at 0 plus? This is V naught at 0 plus, and we've already decided that that was 50 volts. Okay, evaluate this at t equals 0. We end up with that. All right, the next thing is, we probably need the derivative involved here, dv naught dt. Okay, so this dv dt evaluated at 0 plus isn't going to be 0. It's going to be I sub c at 0 plus divided by c. So take the derivative of our thing up here, and we end up with c times d3, I'm sorry, that's minus alpha d4, and that's equal to I sub c at 0 plus. That's the negative 0.1 amps divided by 40 times 10 to the negative 9th Farad. Okay, now why did I do negative? Because here's I naught, it's going up that way. So that's why that negative sign is necessary here. It's going into the negative terminal of the capacitor. Okay, so we know what C is, you know what D4 is, you know what alpha is. We should be able to solve for D3 out of that. And I'll just jump to the solution and tell you that it's 2.5 times 10 to the 6. All right, at this stage we are ready to write V naught as a function of time is going to be 2.5 times 10 to the 6th t e to the negative 10 to the 5th t plus 50 e times 10 to the negative 5th t volts. Okay, so we've done that one problem. All right, let's do another problem. I'm going to draw this one out. I'm pausing the video. I'm going to draw this one out. Okay, here's our problem. What we want to solve for is the voltage across that resistor as a function of time for all times. Before t equals 0, you see these switches are in their current positions the way that I've got them drawn, and at t equals 0 they flip over. So after t equals 0, what we have is this central part here. We've got an R, an L, and a C all in there, okay, in the central region. But before t equals 0, this resistor has no voltage across it. It's isolated out by itself. Before t equals 0, you've got really two different circuits here. You've got that circuit that will allow us to figure out what the charge is on the capacitor there. In fact, it's going to be 15 volts. You can tell that. So at t equals 0, that's going to have 15 volts on it. Then this flips over, and before t equals 0, this has some current going through it, and we could say the current is going up or the current is going down. It doesn't really matter which way we say the current is going as long as we're consistent with it. So if we draw it this way, we have to say that that is 60 milliamps. If we drew it the other way, we would have to say it's negative 60 milliamps. But since the switch is over here, and after a long time, the inductor is going to behave like a wire, so it's going to have all the current, and it acts like there's a short then across that. Okay, so we really have some of our initial conditions figured out just by looking at it that way. Before t equals 0, the voltage across the capacitor at 0 plus then is going to be 15 volts. And we can say that this current I naught is going to be 60 milliamps, going up through it like that. Okay, and we got that from isolating the two sides here. After t equals 0, then we end up with this as our circuit. Like that. 62.5 millihenry, 100 ohms, and 1 microfarad, like that. Okay, now the initial conditions then, 15 volts, I sub L. Okay, now let's talk about this I sub L. We drew the I sub L going upwards here, but when we worked our problems and we were talking about how the currents leave that top node, we said that's I sub C and that's I sub R and this is I sub L. We had I sub L going in that direction. So if we're going to stick to what we've been talking about all of this time, then we need to realize that I sub L at 0 plus, this I sub L is going to be negative 60 milliamps, okay, because we drew it upwards like that. Okay, now that shouldn't be too big a deal. I sub R at 0 plus, let's see, well, what's that going to be? That's just going to be the voltage at 0 plus divided by R. Remember, the current and the voltage for the resistor can change instantaneously. So that's going to be V at 0 plus divided by R, which is 100 ohms. So that's 15 over 100. That's 150 milli. Yeah. What about I sub C at 0 plus? Well, you can figure that out. It's going to be minus I sub R at 0 plus minus I sub L at 0 plus. So what is that? Minus 150 milliamps minus a negative 60 milliamps. So what is that? 90? Negative 90 milliamps. Okay, so we figured out what all of our initial currents are going to be. We got our initial voltage as well. How about what we haven't decided what case this is yet. So let's go ahead and do that. Alpha, this is a parallel, so it's going to be 1 over 2 RC. That's going to be 1 over 2 times 100 times C, which is just 1 times 10 to the negative 6. That's going to be 5,000. And then omega naught squared is 1 over LC, and that's going to be 1 over 62.5 times 10 to the negative 3 times 1 times 10 to the negative 6. That turns out to be 16 times 10 to the 6. Now this was 5 times 10 to the 3, so that alpha squared is going to be 25 times 10 to the 6. Okay, so we've got alpha squared larger than our omega naught squared. That's the underdamped case. So V naught is going to be V final plus A e to the S1t plus A2 e to the S2t. Okay, our V final, we've already, you probably can figure out what that is, and that's going to end up being 0. Why is that? Because all of the energy is leaving the system. This is going to be a natural response. So all of the energy is leaving the system, so that's going to end up being 0. The S1 and the S2, those can be computed pretty quickly here. Let's see, S1 minus alpha plus the square root of alpha squared minus omega naught squared. That turns out to be minus 2,000, and S2 turns out to be minus 8,000. Okay, and both of those are radians per second. So we've got our S1 and our S2. We still need to figure out what A1 and A2 are, and we have to rely upon our initial conditions for that. V naught at 0 plus, what was that? According to our initial conditions here, V naught at 0 plus is 15 volts. So that's 15 volts. And then we evaluate our voltage function at t equals 0. The exponentials go to 1. We're left with A1 plus A2, like that. All right, the next one, d V naught dt, evaluated at 0 plus, is going to turn out to be I sub c at 0 plus divided by c. And I sub c at 0 plus, that's the negative 90 milliamps. So negative 90 milliamps divided by c, and I've forgotten what c is. It's 1 micro. Okay, so 1 times 10 to the negative 6 farads. All right, now that's equal to our voltage function. Take the derivative of it and evaluate it at t equals 0. And hopefully you've done it enough now that you recognize that's going to be S1A1 plus S2A2. And here then our two equations that we can use to evaluate A1 and A2. And I will jump to the solution. You really should practice that though. A1 is going to be 5, A2 is going to be 10. Yeah, that's right. According to my notes, that's right. So V of t is going to be 5e to the negative 2000 t plus 10e to the negative 8000 t volts. Okay, now at t equals 0, the exponentials are going to go to 1, so that's going to be 15 volts. So at t equals 0, we're going to get 15 volts. Is that what we got? Yeah, that's what we got. Okay, so we solved that problem. You could be asked for any of the currents. What is I sub c? What is I sub r? What is I sub l? The same general approach would apply. The trickiest part of this, to be quite honest, is not the math, I don't think. It's determining what the initial and the final conditions are going to be. But if you can do that, you should be able to solve any of these types of problems. We are finished at this point talking about RLC circuits that have a constant voltage or current source. We're going to turn our attention next time to sinusoidal sources, and we're heading towards a discussion of what is known as the sinusoidal steady state. So we're doing sinusoidal steady state analysis from this point going forward for at least the next several videos. All right, so keep that in mind. If you don't know what that means, you should probably read the textbook so that you can have a heads up on it. Have a good one.